Just set a timer. So although I've asked you to have your calculator out, okay, see, we have the same one. You have to remember that Newton and Leibniz and all those guys, they didn't have calculators. And so they had to be creative about how they were going to solve some of these problems without having the access to, oh, quick, what's the log of 17? Or, oh, quick, what's the square root of 53? Or, oh, quick, what's the tangent of 19 degrees? Like, they didn't have calculators to do that, and so they needed to come up with other methods. So we're going to look at how they approached some of their those tough math things and how we can use calculus, how they used calculus to simplify that for themselves. So we're going to talk about Newton and Leibniz's methods today for approximation and how calculus was a big tool in helping them improve their math. So Newton's method was a method he called of linearization. It relied on, oh heavens, what was that? All right, here we go. It relied on y minus y1 equals m times x minus x1. So Newton decided to use a linear line or a linearization, but instead of m for slope, what had Newton just discovered that he could use for slope? The derivative. So instead, Newton swapped out m here for his invention or development of a derivative. And he called that a linearization. So he took a point and he took a slope, which is just like doing a tangent line. Leibniz relied on his differential. And so he relied on separating dy dx into a dy separate from dx, just looking at those two things separately. So they each took their own method and they used that method for approximating things. So they could figure out, oh, what is the log of 17? And they actually could use their derivatives to help them out. All right, can you barely see that I've got a dot right here? Can you see that there's a red line on there? Okay, so the blue function curves. The red one is supposed to be straight as the tangent line. So the red is the tangent line. The blue is the function curve. Newton's idea was, if I need to find that point on the function curve, that might be hard because the curve could belong to a trig function, the curve could belong to a log function, the curve could belong to an inverse secant function, like the curve could be a crazy curve. For him, he was like, I'm going to use the line instead, and to use the line, I'm going to use my own y minus y1 equals f prime of x, that was his derivative, x minus x1. I'm going to use a tangent line instead. And his argument was his tangent line was just as good as the function curve, close enough. Like within thousands of decimal places that it was close enough. That was his argument. So he's like, why would I bother using a complicated curve when I could just use my tangent line? And you know what? I'm going to be in the ballpark of within thousandths of accuracy. So that was his philosophy. That was his approach. So he just calculated a tangent line. He called it a linearization, but he was just doing a tangent line. He used the point and the slope, and he came up with the equation, right? So he took his point, xy. He took the slope from f prime, and he wrote the equation y minus y1 equals f prime of x times x minus x1. And that's what he used instead. So I'm going to show you how close Newton was. It was brilliant, his idea. Okay, but he called it linearization. It's the same thing as tangent line. It's exactly what we did. Now, If you start following his tangent line far away from the curve, then the accuracy drops off. So if you're using it right here, you're fine. But notice the gap that grows here in between the tangent line and the curve. The gap gets greater and greater the farther away you stray. And so his was only accurate within, you know, a small region. If he needed to go somewhere else, he'd have to create a new tangent line at a new place. So in other words, he couldn't stay on his tangent line out here and expect accuracy. What he should do is move back over to the curve, calculate a new tangent line, and do that. So he was recalculating tangent lines anywhere he needed them. You can't just use one tangent line and be done. He also recognized that concavity was part of his advantage. The curve that I'm drawing here, the blue one, what kind of concavity does it have? Has positive concavity. The tangent line, because it's straight, has no concavity. A tangent line underneath positive concavity is always going to be below. Okay, the way the curve of the concavity goes, the red tangent line is always going to be below. So Newton knew that his estimate, although would be very, very accurate within thousands, he always knew he was going to be slightly below what the actual real value was because of the concavity. If he was working with a different concavity, he might know his estimate was slightly above. So depended on that, he always checked his concavity. So the gap grows. Oh, so that was the next one. The concavity determines whether or not his value that he found would be slightly too big or slightly too small. So you, and the same thing, would need to make an argument. Once you find it using Newton's method, you'll say, yeah, this is hyper accurate, but still ultimately it's going to be a smidge too big because the concavity is actually concaving down. So my answer would be slightly too big. Or if it was concaving up, your answer would be slightly too small. Depending on which direction you go, sometimes the concavity is different on either side. So if you were following the tangent line and you were sitting right here, you would say, my tangent line, because it's on the left, my tangent line will produce an answer that is too big, slightly, because the concavity is down. Or on the other way, if you were on this side, that answer there would be too small or an underestimate because the concavity was positive. So you have to check the concavity as well. All right, so let's actually do it. All right, here we go. We are going to compare what Newton did and what our calculators can do. So you have a quartic function to work with, 2x to the fourth plus 4x minus 3. Okay, figure out the value of negative 0.9 without a calculator. So the option you would have, let's start with actually option 2. F of negative 0.9 means doing 2 times negative 0.9 to the fourth plus 4 times negative 0.9 minus 3. It's not impossible, but it's laborious. You certainly could take 0.9 and square it, and then cube it, and then multiply it to the fourth power, and then multiply by 2. You could do it, okay, without a calculator. However, Newton is saying, I can do it faster. I can do it faster than any of you, and I bet I'm going to be like super pretty much accurate. So let's try see how Newton would do it, and then we'll actually check on the calculator and see how close he was. All right, so we're going to ditch that, and we're going to do Newton's method. So Newton would say, I'm going to use a point, and I'm going to use my method to find slope. All right, Newton would say, forget that. I don't want to use negative 0.9. It's too far away. What point do you think Newton would use that would be reasonably close? He's going to use negative 1, okay? You got any problem plugging negative 1 into that equation? Nah, we can plug negative 1 in. So plug negative 1, take it to the fourth, multiply it by 2, add 4 times negative 1. You should be able to figure that out mentally. Okay, what do you get for your answer? Negative 5. Okay. All right, and then we're going to say, all right, we'll use Newton's method to find the slope as well. The slope is going to be 8x cubed plus 4. And I'm going to figure out my slope on that. Excuse me. 8 times negative 1 cubed plus 4. That's negative 8 plus 4. That's negative 2. Sorry, negative 4. All right, then we're going to write our linearization, which is just another word for tangent line. So the linearization would be y plus 5 equals negative 4, bless you, times x plus 1. Now, let's plug negative 0.9 into that. Rather than plugging negative 0.9 into the original quartic equation, plug negative 9 into this one. It's a lot easier. If I plug negative 9 in, I'm going to have negative 4 times negative 0.9 plus 1, and I'm going to move my minus 5 over to the other side. So I just pulled the plus 5 over to the back and put it as a minus 5. What's negative 0.9 plus 1? Positive 0.1. And what's positive 0.1 times negative 4? Negative 0.4 plus 5, which is negative 4.6. That's positive 4.6. Sorry. Erase. Not erasing.
How are you checking? -5.
Oh, minus 5. Hello. Let's try that again. I changed it on my. Okay, let me erase. There we go. Minus 5. Negative 5.4. All right, so Newton said, hey, bet you answer is probably pretty close to negative 5.4. Okay? All right, now grab your calculator and actually plug negative 0.9 into the original function and tell me how close Newton was. Okay? All right, so go to the next slide. Newton's approximation, we're saying is negative 5.4. Newton would have known if that was an over or under estimate based on the concavity. Let's check what the concavity is. So we need the second derivative to check the concavity. We already knew what the first derivative was, right? The first derivative was 8x, bless you, 8x to the third plus 4. So the second derivative is 24x squared. What would be true about all the concavity of that? Why is it always positive? Okay? That's always positive. If the function is always positive, then the tangent line that Newton drew would be underneath something that had always been positive. Newton's tangent line, Newton's linearization was under the positive concavity. So Newton's linearization would always underestimate. And he knew that, and he was willing to concede that an underestimation, he was satisfied that as long as he knew it would be a little bit under the actual value. And so then, yes, you actually checked it with your calculators. Negative 5.4 is less than negative 5. What did it turn out to be? 5.287. Okay, so yes, he was a little bit under, but he wasn't off by much. And in his day and age, that amount of accuracy down to the decimal place, down to the hundredths of a decimal place was acceptable. You can hardly, with what they were measuring, they couldn't measure much more accurate than that. All right, so let's do it again with a trig graph. Okay, so use the linearization, make a linearization like Newton would, and approximate cosine of 1.75. So Newton would say, forget that. I don't want to use 1.75 because 1.75 is not a good trig number. He would pick something that was decently close to 1.75, and I've got it labeled for you. Okay, he's going to pick the point 1/2. Okay, 1/2 is in the ballpark of 1.7. If you know 1.72, okay, so if you know what pi is, you know that 1.72 is pretty close to 1.75. So that was his point. What would the y value be for Newton's point? 0. Yep. Okay, Newton's slope is going to be using Newton's derivative. The derivative is negative sine of x, which is negative sine of pi halves, which is -1. So Newton's linearization using his point and slope would be y minus 0 equals -1 times x minus pi halves.
You get the slope by taking the derivative of the...
Yep,
Okay.
yep, I did the slope by finding f prime. That would be Newton's way. Okay, now plug 1.75 into this. Okay, plug 1.75 with the actual number into this equation. Well, actually, let's decide if it's going to be an underestimate in the first place. Looking at our graph, this is 1.7. Yeah, close. 1.707. Okay. So 1.75 is going to be over here. So what kind of concavity is existing on that side? The concavity on that side? This is positive concavity here. Okay, so that side has positive concavity. And so if you're having positive concavity on your function, the tangent line will always skim underneath. So based on positive concavity, a tangent line will underestimate. Okay, so this is going to be an underestimate. Because f of x has positive concavity. At x equals 1.75. Yeah.
What do you send 1.707 is?
What's the value? 1.577, thanks. 5? Wait, 1 point. I'm missing my 5. All right. Okay, so we know we're going to be an underestimate. So let's actually check it all the way. So now we're going to plug in 1.75 into our value. So y equals -1 times 1.75 minus pi halves. In other words, 1.75 minus 1.570. You said I was rounding wrong. It was 8 instead of 7? Okay. Okay. We can probably even do as accurate as 1.57 would be fine. So 1.75 minus 1.57, we're estimating that the value is going to be negative. All right, and then you just do the subtraction. 0. What's 7.5 minus 5.7? 1.8. So that is the estimate of what that actual value was. Okay, now grab your calculator and use it to check what is, in radian mode please, what is actually the cosine of 1.75. So this is what what Newton predicted the cosine of Okay, so Newton's prediction of cosine 1.75. He's saying negative 0.18. So what's the actual? What is it? Negative 0.1, say it again. 78. All right, so now he's only off by 2/100ths of a decimal point. Okay, so he's pretty close. Newton's prediction versus the actual value. All right, how would Leibniz have done it? All right, Leibniz used dy dx. So his approach was slightly different, but he's arriving at the same thing. He called them, these pieces, differentials. So instead of calling it slope, together they make slope. Separately, they're called differentials. And he's saying I can move them around. I can separate them from each other and I can look at them independently. Did you guys do vectors last year? Yeah? In vectors, you're allowed to look at how do I change something horizontally without changing it vertically? Or how do I change it vertically without changing it horizontally? Or if I change both, then what changes happen? That's kind of where Leibniz was going a little bit. So every differential represents changing that single variable in and of itself, and it's going to have an impact related to another variable. So here's how he would say it. Okay, the radius of my circle, I'm going to increase it from 5 to 5.1. How will that impact the area? What will that result in? If I make that one change, what will the result be? Kind of like a coach. Ooh, I'm going to change this one player. If I change this one player, how will that change my offense altogether? Will that have a result? Will it be positive or negative? Be a good thing or bad thing? All right, so here's what Leibniz would do. He'd say, all right, we're going to start with area, pi r squared. He would say dA dr, not t, we're not doing time, we're not doing anything as a motion right now, it's dA dr, is 2 pi r times the chain rule of dr dr. Okay, did you follow that, how Leibniz would do it? dA dr on one side, dr dr on the other, and what's dr dr? 1. Okay, so then we can simplify and say, all right, dA over dr is just simply 2 pi r. And then he understood that these little pieces, the dA and the dr, could be separated from each other. So he could take that dr and put it over here, multiplying basically. So 2 pi r times just plain dr, like that. So that he had no denominators. Basically, I don't want denominators anymore. The d is called, those are called differentials. And what they do is you can change one but not the other. So dA would be, I'm going to change just the area and see how it impacts the radius. Or dr would be, I'm going to change just the radius and see how it impacts the area. All right, that's what our question is. The radius of a circle is changed from 5 to 5.1. How will that impact the area? So dA is equal to 2 pi, r is 5, and then dr is how much it is being changed by. So how much is it being changed by? 0.1. It's not, don't put in 5.1, put in how much is it changing by. So that gives me 10 pi, that's 2 times 5, times the fraction 1/10, in other words, pi. Does that mean the area is pi? What does the pi mean? It means how much the area will be changed by. So whatever the area was, it will be changed by a value of pi. So look at that. You changed the radius by how much? 0.1? And that resulted in changing the area by how much? 3.14. So you changed the radius by a 0.1 decimal, 1/10. And it ended up having a large impact on the area, and it got changed by 3.14. They impact each other. So you're like, it's just one little thing. I'm just gonna change one thing. or I'm just going to do this one thing, it has a big impact, or it could have a big impact. That's what Leibniz wanted to know. How much of an impact would it be? How risky is it? Let's try another one. If you're on a kinetic function, x to the 5th plus 2x, and you change your x by 1/100th, is that a risky change? How much of a change will it happen? All right, so Newton would say, or Leibniz would say, dy dx is then going to be 5x to the 4th plus 2. The differential would be dy equals 5x to the 4th plus 2 quantity dx. The quantity is important, because if you only throw the dx and it only is next to the 2, that's going to mess everything up. You want to have the quantity of dx. So then, dy is going to be equal to 5 times 1 is, or x is 1, and the differential is 0.01. In other words, 7 times 1/100th, or 7/100ths. So if you interpret this, the values of the differentials, the x differential was 1/100th, the y differential is 7/100ths. So that means if you change your x by 1/100th, the resulting impact is your y will be changed by 7/100ths. So it has a greater impact. Over or underestimate is the same idea as what's the second derivative. So d2y, finding the second derivative of this, is 20x cubed. 20x cubed is positive when x is 1, which means it has positive concavity. Positive concavity always results in an underestimate of your value. Okay, the positive concavity means that's pulled higher than what your tangent line would be. Underestimate. Positive doesn't mean an overestimate. Positive concavity means that the function is higher than the tangent line. So your value is an underestimate. All right, any questions on that? Okay, great. Okay, so then find a partner for the last